So I've been in love with security ever since I was a little kid. As an early teen, I went to almost every 2600 meeting. I had a stack of free Kevin stickers that I put on pretty much everything I can get my hands on. I built a pirate radio station, and I had a lot of fun with that. And I just loved taking things apart and figuring out how they worked. After working on Wall Street for a few years, I came back to Columbia to do a PhD program to think about ways to defend and exploit embedded systems. Doing this type of research at Columbia is exactly the right environment to be in. We're supported by various agencies within the government who really have an interest, who honestly care about improving the state of embedded security. And we definitely have a lot of freedom inside an academic institution to pursue this line of research, which can be at times sensitive because we are dealing with security vulnerabilities within devices that are ubiquitous, that are used all over the world. Hello, my name is Ang Cui. I am a PhD student at Columbia University, and I am a member of the ACM. I like to point out, so this thing looks like a phone, right? But really, in reality, this is a tiny little computer that's shoved into a plastic case that makes you think that it's a phone, but it really is a general purpose computer. So these things can be attacked and exploited just like general purpose computers can. And once you compromise a device like this, there is no way to detect whether this thing has been compromised or not. So there is no host-based defense on this phone whatsoever. So once you have access to this phone, you gain a foothold into the network that you want to penetrate, and then you can start attacking general purpose computers and other embedded systems from within the network using, let's say, a compromised phone. Now that's very attractive because let's say the network administrator noticed that the general purpose server has been compromised. The first thing that person will do is wipe the server, rebuild it, fortify it, and if you only went after the general purpose computer, you would be kicked off the network at that point. But if you attack that computer with a phone, right, once the server goes away, you still have a foothold in the network, and you can regain access to that server through a telephone inside the network. Not to mention that these devices, aside from being just little computers, also have eyes and ears in very sensitive rooms all over the world. So that's another reason why we think this is interesting. Back in the day, there was a typewriter inside the US Embassy in Moscow. And for some reason, a very nice man decided to X-ray this typewriter. And what they found was that the undercarriage of this typewriter was actually hollowed out, and tiny little pieces of electronics was replaced inside this aluminum bar to detect the spin of the typewriter ink ball to predict the letter that was being pressed on the typewriter. And that information was being transmitted by a tiny little transmitter to a listening station out on the street. So someone actually bugged this typewriter to listen for all the things that was typed inside this embassy. Now that was something done with 1980s technology, right? So that was something called Project Gunman, which was recently declassified. Now, in 2012, 2013 technology, we can do exactly the same thing, but it has become much simpler. I wanted to introduce my defensive mechanism inside printers because the work that I did on the Symbiote defense technology was mainly focused on CISCO routers. And I wanted a second type of device just to prove that that technology would work on something that's not a router. So I looked at printers. And the very first thing that you have to do when you do Symbiote defense is to figure out a way to modify the firmware of the device that you're working with in order to inject Symbiote technology into it. So I started looking at the printer to find out ways that I can change the firmware, and it turns out the standard way of firmware update on these printers is by simply printing documents to it. When I realized that, I thought, well, this is a really zen way of doing it, right? How does a printer update its firmware? You print to it. Once I verified that, the attack was almost trivial, right? Now all we have to do is understand the RFU update format, package our malware in exactly the same way, and send it along as part of, let's say, a PostScript file. Now, I don't think I'm the first person to have come up with this. And the interesting question about this attack isn't how it works. How it works is pretty trivial, but how many times this has actually happened in the past, and if there is actually a way that we can detect or audit a printer to see if it has been compromised. Now, this printer in the back, it will print documents just the same way as any other printer. It will blink the lights in exactly the same way. Right? It will, answer all the buttons that you press. But you have no way of knowing whether that printer is running the firmware image that it's supposed to. You have no way of knowing that there's no rootkit or malware that's actually spying on the information that's being printed to the document or being used to attack other parts of the network. The most immediate thing that you notice about the phone is that it has a microphone on it. So you can hear, in theory, what is being said in the room even when you're not on a phone call. Now, here is your typical Cisco IP phone, right? It's in the shape of a telephone. You think it's a telephone. But when you turn it around, this thing really is a general purpose computer, right? Connected to some flash, connected to the Ethernet port, and connected to some ROM. So this is a tiny little computer that's shoved into a plastic case that makes you think it's a telephone. One thing to notice is that here is the microphone that's connected to the computer, and there's no mechanical switch to shut off this microphone. So if some person came along and found a vulnerability inside this phone, in theory, you should be able to listen to what's going on inside the microphone, even when the phone's sitting on the desk doing nothing at all. Here is a demo of a compromised Cisco phone. You find these all over the place. We use this little physical device called the thing cloner. It's very simple. All it is a RJ11 to RS-232 to Bluetooth adapter. Now, I plug this thing in for about 30 seconds. I use a smartphone to transmit 900 bytes of data through this Bluetooth device to the console, to the phone. And the purpose of that is to trigger a kernel vulnerability that gets me root access to the device, where I then patch the DSP and the JVM so that I can listen to whatever this phone is hearing when it is on or off a phone call. So right now, this phone is listening to everything we say, and it is sending that data across the network to my laptop. Now here is VLC playing this data on the network. And I spent the first 3 years of my PhD career thinking about ways of defending Cisco routers and routers in general against attack, and coming up with ways of writing exploits and rootkits for these routers. They are incredibly vulnerable. So if you look at the way this operating system works, the closest popular analog I can come up with is DOS. So in a lot of real ways, the Cisco routers that runs a large portion of the internet infrastructure, they're basically special purpose ugly boxes that runs a very DOS-like operating system. You have none of the modern protections that you would find in a modern kernel inside these devices. And it turns out they are fairly simple to exploit with one problem. There are actually 300,000 different firmware images running on Cisco routers today. So compare that to maybe the dozen of popular operating systems we find on desktops and servers. That makes exploitation a little trickier, right? Because you have no idea which kind of binary layout of the exact router that you're going to go up against is, even if you have an exploitable vulnerability. So a few years ago, I wrote this cute little rootkit that overcomes exactly this problem. What it actually does is it scans through the memory range of the router, and it fingerprints the memory layout, and it figures out exactly which version of the Cisco router we're on, and then we attack the router as if we knew precisely the memory layout of that device. But here's a funny thing, so if you look at the product offering of these routers, they have, and the firewalls and switches, they have a lot of features that will protect the computers behind the router and the firewall from exploitation. So an attacker would come along and maybe try to send you a spam email or something like that. Sometimes these devices will actually filter that out and protect the computers behind it. But what's to protect the routers from exploitation, right? There is nothing there. So that's what I spent the last 5 years of my life really thinking about, ways to defend these vulnerable embedded systems that run all of our infrastructure from attack. So software symbiote is really what I've spent the last 5 years of my life thinking about, and it is my solution to a real host-based defense solution for securing arbitrary embedded systems. The easiest way to think about software symbiote is to think about an analog you find in biology and nature, right? So this is a biologically inspired mechanism that mimics symbiosis in nature. So for example, you have, let's say, two living organisms that coexist together for mutual benefit. And a good example of that is, the clownfish that lives inside the reefs that protects anemones against tiny little creatures that the clownfish eats, right? So these are two individual biological organisms that live together to secure each other against the predators that they both face. Another example is, the vent worm, right? So there is this bacteria inside the digestive tract of the vent worm that is responsible for breaking down the nutrients so the vent worm can live. So in that case, it looks like there's a single living organism, but in reality there are two types of organisms that have to coexist for mutual survival. The reason why I took that inspiration is because when it comes to securing embedded systems, the very first challenge you have to overcome is the matter of diversity, and the matter that you don't really understand what it is that you're exactly trying to protect to the granularity that you can understand a general purpose computer, a well-known kernel. So in order to still offer some security, we think about the embedded device as a living organism, and we think about the symbiote as another organism that is introduced to this mysterious organism so that they can both coexist and provide mutual benefit. Now, the benefit that the host program, let's say the host organism, I'm going to call it the host program, provides to the symbiote is that the symbiote is allowed to extract computational resources away from the host program, right? And what the symbiote provides in return is it computes various security properties like firmware integrity. So as the host program runs, the symbiote also runs, and the symbiote verifies that the host program hasn't been compromised or tampered with. And if the symbiote is tampered with, the host program will then stop operating correctly. And as long as the symbiote operates correctly, you can have a guarantee that the host program hasn't been modified. The way the symbiote is designed is it's actually two pieces, two components. There is a symbiote manager that is injected into the host program that is responsible for executing various symbiote payloads. Now, the first payload that I talked about is this firmware integrity verification payload, which computes the integrity of the firmware, continuously making sure that the firmware hasn't been modified. So that's one specific payload that you could use inside the symbiote system. Switch in another payload, you can compute something different. So anything that is computable within the host program, the symbiote payload can compute using this way. So another thing that we can compute is an anomaly detector symbiote payload, which will look at features that tell us how the host program is running, so the patterns of its execution, to detect whether that execution pattern looks normal or not. Now, this is a mechanism, or this is a technique that's been used in general purpose computers with varying success. But here on the embedded system side, we actually have a very interesting advantage in that while this is a general purpose computer, the task it's performing is really special purpose. So what it's supposed to be doing is very easily recognizable compared to all of the various different tasks you would have to perform on a general purpose computer. So here, creating an accurate anomaly detector inside an embedded system is fairly accurate compared to what you would get on general purpose computers. We call it ABSR for short. But here's a really simple idea, and this is something that my mom talks to me all the time, right? When you're not playing with your toys, put it away, right? Like if you don't wear your clothes, don't keep it on the floor. So here, is something that is a fairly simple idea. This device, and let's say your Netgear router or any little embedded doodad you've bought over the last 2-3 years. On the box, it'll say it supports every single protocol, every single feature under the sun. I mean, you could, stream straight to Netflix. You can post on Twitter. You can do all sorts of various networking protocols, and it all looks great on the box. But when you take it home, all you really care about is that the thing has Wi-Fi. You can connect to it, and it works. And you stick it in the closet. And you don't think about it ever again. Now, even though you don't use these features, that feature is either active or deactivated, but it's still inside the binary of the device that you're working with. Now that is something that an attacker can use to break into the embedded system. So the idea is you look at the configuration, you look at the code, the binary of the firmware, and you literally remove all of the binary from the features that are not needed. Okay, so this is what we call autotomy. This is another biological phenomenon where a living organism will shed a part of its own body in order to survive. So you think about the little lizard that you can cut off the tail, and the lizard will run away and the tail will stay behind, right? That's a way to save the lizard's life. So in autotomy, we are actually taking out unnecessary binaries from the embedded devices by looking at the configuration to see what's not needed. Okay, so this way, the device will use less memory and will have less code that can be used by the attacker to break into the system. And we can do this in an automated way without affecting the functionality of the device at all. In the general case, this is an intractable problem. But it turns out, in the practical case, code is written usually, from all the system we've looked at, rationally enough that you can come up with a combination of dynamic and static analysis to figure out exactly which portion of the code corresponds to which features within the system. Now, we've tried this on CISCO routers, we've tried this on printers, and it seems to be fairly, I wouldn't say easy, but it's certainly a doable technique to figure out which parts of the code can be removed and which ones cannot be. So the very first public demonstration of Symbiote defense is on a CISCO 2821 router. Now, we demoed this, I think, last year, and we're delivering a sensor to DHS so that they can start testing this device in their own network. Now, the idea there isn't just to detect exploitation on the router. We're going one step further. We're actually allowing the attack to happen, and we're periodically pulling the memory layout of the device to a third-party server to analyze exactly what the exploit is doing, what the malware is doing. So we're turning this into you can say, a passive honeypot sensor of an embedded device that's actually running on the physical hardware of the embedded device itself. So we can put this device out on the network, wait for this device to be attacked, and capture all of the offensive code that the adversary throws at us. So we will understand exactly how our embedded systems can be attacked, and then come up with defenses to mitigate that. And also, both of the technologies I developed, Symbiote and ABSR, is designed to work without requiring proprietary information from the vendor, without requiring source code. And this works at the binary level, and I did that specifically in order to, what I consider to democratize embedded security. Now, if you think about the way embedded security works today, here's really just the process. Someone, maybe the vendor or maybe some researcher, finds a vulnerability, alerts the vendor, and the vendor has the entire burden of coming up with a security patch. No one else can do this because the vendor does not allow anyone else to modify their code. So you wait an arbitrary period of time for the vendor to either come up with a good patch that fixes the problem, or come up with a terrible patch that really does nothing, as we've seen with the CISCO patch that was just recently released. And that's the way embedded security is done today. What I would say is that there's not all that much difference between the software written for embedded systems and software written for general purpose computers. We have learned a lot over the years about ways of writing secure code, ways of making our code less buggy. But at the end of the day, there will be bugs inside software written by human beings, and there will be ways to exploit those bugs to make systems do what they're not supposed to. There's one major difference between the code that runs on general purpose computers like laptops and servers and code that runs on embedded systems. And that is, on the servers and on your laptop, there are software mechanisms that will protect the host, the program against exploitation, like antivirus, endpoint protection, anomaly detectors that run in these systems that is essentially a second line of defense against exploitation for when the software that we write fails. This does not currently exist on embedded systems, and that's the major difference. And in the future, ask yourself, why shouldn't host-based defense exist on embedded systems, right? And right now, it doesn't exist because the state of the art in technology in defending embedded systems is not ready, but this is exactly why I think technologies like software symbiote and ABSR will allow a new generation of host-based defense security products to be placed onto embedded devices that we use every day.